Good morning, everyone. Welcome to my presentation on attenuating heat transfer through residential roof assembly. My name is Christopher Tan, and today I will be presenting our evolution of bark insulation material based on six-dimensional building information modeling. This work was conducted in collaboration with colleagues from Jadara University, Yamrock University, University Technology Petronas, and NextGen's Carbon Solutions. As we gathered here at the International Conference on Digital Technology Driven Engineering 2025, our goal is to show how digital simulations helps solve a very physics problem, thermal comfort in the tropics. Let's begin with the content. As many of you know, Southeast Asia is a region defined by its intense climate, year-round high temperature and high humidity. In this region, the predominant housing topology is the low-rise home. While these structures are culturally and economically significant, their design often expose a vast amount of roof surface area to direct, intense solar radiation. Why is this a problem? Physically, heat is absorbed at the roof surface. Through the process of conduction, the heat travels inward, penetrating the roofing materials, heating up the attic space, and eventually radiating into the living areas below. Our baseline data shows that uninsulated roofs are a major weak point in the building envelope, allowing substantial heat gain. This doesn't just make home uncomfortable, it drives up energy costs for air conditioning. To combat with this, we focus our study on bark insulation. We looked at specifically at three common materials: fiberglass, mineral wood, expanded polystyrene. These materials work by resisting conductive heat transfer, essentially trapping air pockets to slow down the movement of heat into living spaces. We measure this effectiveness using the R value, where a higher value of R indicates better resistance to heat flows. This study evaluates how different bark insulation materials can slow heat transfer into living spaces under tropical conditions. Moving on to our methodology, we utilize six-dimensional building information modeling (BIM). Specifically, we employed the IESVE Integrated Environmental Solutions virtual environment software to generate our models. We selected three specific locations to represent the climates: Bandar Seri Begawan, Kuala Lumpur, and Singapore. For the building model itself, we modeled a standardized test cell measuring 4 meter by 4 meter by 3 meter. This complied with the Uniform Buildings Bylaw (UBBL) 1984, ensuring our results are relevant to actual building codes in the region. We also integrate accurate weather data sourced from Energy Plus to ensure our environmental variable, solar irradiance, wind speed, and ambient temperature were realistic. You can see the representation of the test cell with the red roof tiling in the figure up here. Now, let's look at the result, starting with attic air temperature. By our simulation, mineral wood achieved the greatest temperature drop overall. If your primary goal is reducing a raw temperature of the air inside the attic, mineral wood will be the superior performer. However, we found an interesting nuance regarding the EPS. While it didn't quite match mineral wood in the raw thermal reduction, it performed surprisingly well in highly humid conditions, such as those modeled for Singapore. This largely due to its moisture resistance, which we will discuss more in a moment. Overall, all insulation types of significantly reduced attic temperature compared to the uninsulated roof condition. Next, we examine the ceiling surface temperature, which directly affect indoor thermal comfort. This is the feed you feel radiating down on you. Look at the differences here. Insulated ceiling consistently maintain the temperature in range of 30 to 32 degrees Celsius, whereas the uninsulated ceiling temperature increased up to approximately 39.5 degrees Celsius. That is a drop of nearly 10 degrees. Although EPS shows slightly higher ceiling temperature compared to fiberglass and mineral wood due to its lower thermal mass, it still provides an improvement over the uninsulated case. This demonstrates that bulk insulation is effective in reducing heat transmission to occupied spaces. From the analysis, the installation of bulk insulation resulted in a 70 to 85% reduction in U values, indicating a significant improvement in thermal resistance. Fiberglass and mineral wood exhibited superior thermal performance compared to EPS, mainly due to their lower thermal conductivity, ranging between 0.032 and 0.040 watts per meter Kelvin, compared to the 0.038 and 0.045 for EPS. However, EPS remains an effective option, particularly in high humidity environments where moisture resistance becomes an important advantage. Kuala Lumpur and Singapore, which share similar equatorial climates, shows comparable temperature reduction when insulation was applied. This is important to note that prolonged moisture exposure can degrade the performance of fiberglass and mineral wood if vapor sealing is not properly implemented. In conclusion, bulk insulation is highly effective in reducing heat transfer through residential roofs in tropical climates. However, material selection must be considered. Local climatic conditions, particularly humidity levels and solar exposure. Fiberglass, mineral wood, and EPS are all suitable for adopting in dry to moderate humid conditions commonly found in Southeast Asia. Future study could further enhance performance by combining bulk insulation with radiance barriers or ventilated attic design. Overall, our 6D BIM based thermal simulation confirmed that bulk insulation significantly attenuates heat transfer, improving passive cooling performance and enhance thermal comfort. Among the materials studied, mineral wood is the most effective, while EPS provide a variable alternative when moisture resistance and cost efficiency are prioritized. This finding offer empirically support guidance for optimizing residential roof insulation strategy in tropical regions. The references listed here include key studies on roof insulation, thermal performance modeling, and tropical building design that support this study. Thank you very much for your attention. This is all from my presentation.